So at today's seminar, I'm going to talk about the notion of a homotopy equivalence in the context of homotopy type theory. I should warn you, I am semi-prepared for this. But I would like to explain the basic ideas and the basic observations that you get out of there, of the ideas here. So just to repeat and to get some notation, we're going to have, I'm going to write like this. So I'm generally going to use A, B for spaces. And then if I have a path, P, in a space, so let's say A is a space. A is a space. And then I have points X, Y, and Y in A. Then I'm going to write like this, X, Y, for the space of all paths from X to Y. And then if there is a particular path I want to name, I say P is a path in the space of paths from X to Y. And this is what's called the identity type in intentional type theory. So the question I want to think about is, what does it mean, suppose I have two spaces, when are the spaces A and B the same? And because we're doing homotopy type theory, this should mean up to homotopy, whatever that means. There is a notion of homotopy equivalence in the homotopy theory, the usual notion, and there is a notion of weak equivalence in homotopy theory. But I just want to start from scratch and just think about how you would do this naively if you try to do spaces via type theory, and maybe you haven't seen all the homotopy theory yet. Of course, it's going to be hard to discover certain things without knowing anything about homotopy theory, but let's just try, okay? So here's my first attempt. So the first attempt would be to say, well, in homotopy type theory, everything is up to homotopy anyway. You don't really have a way of saying the 2 points are equal. The best you can say is that they're connected by a path. So the first attempt would be just to phrase as strongly as we can that the spaces A and B are isomorphic in the sense that there are maps going back and forth. So we say, okay, so here's our first attempt. We're going to say spaces A and B are the same if there is a map going in this direction and another one going back, such that something happens. Now, what is the thing that should happen? If we were doing set theory, at this point we would write something like this. F composed with G is the identity on B, and G composed with F is the identity on A. Yes? But how do we write identity? Because we don't have identity, we only have paths in homotopy type theory. So you would say, okay, so in type theory we would require type theory. Now we would require, and just change this with paths. So we require that there is a path from F composed with G to identity on B, and there has to be a map from G to F, G composed with F to identity on A. So you could require that. That would be direct, that's what it means for these two to be identical in homotopy type theory. So if I write this out in full, now I would have to say, just to see where this is going. So you would say something like A is equivalent to B. This is not a fixed notation. This is supposed to be a temporary notation. This means, so in logic you say this means that something holds. So in type theory we're going to say this means that there is a certain space, and we are saying that there's something in that space. So what's the space? Well, the space is there exists. See, I'm going to talk logic, but I'm going to write down geometry. So there exists an F from A to B. There exists a G from B to A, such that F composed with G has a path to the identity on B, cross G composed with F has a path to the identity on A. So we would speak about the space of A and B being equivalent. And then if we say that there's something in this space, that means they actually are equivalent. If this space is empty, then they're not equivalent. But it is also interesting to consider this space. It's a space of things, and we can consider its geometry, in which case we are considering all the ways in which two things can be equivalent. However, this particular definition is too strong, because it's very hard to establish paths in function spaces. This is supposed to give me a path in a function space. And if you look at the rules, there's almost nothing that you can do to create a path in a function space. So we want a slightly weaker definition, and we try to prove the properties of that one. Under certain circumstances, like if you have the univalence axiom, which we haven't talked about yet, then it doesn't matter whether you take this very strong definition or maybe some weak definition, because the univalence axiom allows you to construct lots of paths between functions. But for now, we're going to slightly weaken this condition here. Okay? And I will not keep writing down these sigmas all the time. Yes? So the second attempt would be to weaken the condition that there has to be an actual path. So the thing you want to think about here is, what is the difference between having a path and having a homotopy? So suppose we have two spaces, A and B, and I have two maps between them, F and G. So I can say that there is a path between them. So P would be something that is a path from F to G. Or I can say for every x in A, there is a path from f of x to g of x. And I'll call this one H. Now, in classical topology, both of these are called homotopy. Because this is what a homotopy is. It's a homotopy is a map which for every x in A gives you a path from f of x to g of x. But also this, a path in the function space is well known to be the same thing as a homotopy between two functions. However, we don't know this. In just pure type theory, where you don't have any extra assumptions, we don't know what the connection is. And so we have just used this stronger one in our definition of two spaces are equal, because we require that there be a path. So, but we may also consider this weaker one. So we could write as the space of homotopies. I'm going to write it like this. F is homotopic to G. This will be the space, by definition, we define this to be this space here. Okay, so it's the space of maps, which for every x, there is a map from f of x to g of x. I should warn you that you should imagine that everything is automatically continuous. So in particular, here we have a map which, given a point x, gives me a path from f of x to g of x. The selection of the path has to be continuous with respect to the point. So this really is a homotopy. The following thing wouldn't work. If I take the circle, and then I say, let's consider paths. You know, if you have f of x and g of x, let's say we take f of x to be maybe the identity, and we take g of x to be the reflection across the x-axis. And then you say, well, there always is a path. If I take a point, and I take another point, x, here's its reflection, then there is always a path. You can just go like this. But it's a crucial question. The crucial question is, can you make this path depend on x continuously? If you can't, then that's not an element of this space. Okay? So this is going to be a homotopy, even though maybe it doesn't look like one. If you wrote this in set theory, it would make no sense. It would say for every x, there is a path from f of x to g of x. That's not a homotopy. So now I have the space of homotopies between f and g, and I'll use this one. So here's our second attempt. We would say that A and B are the same if there are two maps between them such that f composed with g now is homotopic in this way to the identity on B, and g composed with f is homotopic to the identity on A. Like that. That's a weaker definition because you can easily show that if you have a path from f to g, then you have a homotopy from f to g. The other way around, you need extra assumptions. So this is a weaker definition now. So if we wrote down the space of these things, we would say, well, what would you call this? You could just call this isomorphism, right? I mean, if you think about this in a set theoretic way, this is just saying that f and g are inverses of each other, pointwise inverses of each other. So I'm going to call this iso. Iso AB, by definition, is the space of all such maps. So I say, well, I have one map, and I have another map, and then I have the space of homotopies like that, crossed with the space of homotopies like that. There isn't much change from what we had before. I just changed the path to the homotopy. But there is a third way you could do this. And that's when you say the homotopy fibers are contractible. Now, to see what that means, you start thinking in the following way. How about trying to explain that A and B are equivalent with using just one map? I don't want to have G, I just want to use one map. So I want to have A, and I want to have F and B, and I want to specify that this is an equivalence if F has a certain property. Now, again, set theoretically, you would say something like F is a bijection. A particular way of saying F is a bijection. So if you say F is a bijection, that's for all exists exactly one. So one way to say that is like this. For every y in B, the space, the inverse image of y contains exactly one element, is a singleton. And so now we try to turn this into a homotopy theoretic definition. So we know already that the for all is going to turn into a pi. But the question is, what is this f to the minus 1 of y? What is that? Well, by definition, this is the set of those x's in A such that f of x equals y. So you just change this equal to path, and you get the following definition, which is called the homotopy fiber. H fiber of f at x by definition is, f at y here, f at y is the space consisting of a point x in A and then a path from f of x to y. Now there is an important difference between this definition of H fiber here, because this is just f to the minus 1 of y. This one is the usual fiber, and this is the homotopy fiber. The difference is the following. If you think classically, then the inverse image f to the minus 1 of y, it consists of x's. It consists of points of A. Yes? But this one is not saying points of A. This one is saying pairs. A typical element in this, what is a typical element in this space? Well, a typical element in this space is some point, you know, like U, together with a path P, which goes from F of U to Y. So it really is a pair. You don't just keep the points, you also remember how you can get from the point to where you want to be. So you have to remember these points. And these points here, these paths here, sorry, the paths. These paths, again, give you extra geometric structure that you wouldn't be there if I just deleted it. Because now I'm in a total space. I cannot just sort of throw away things. And so now we know how to say the inverse image of Y. We'll just use this definition. It's the set theoretic definition translated into type theory. But then we also want to say that something is a singleton. How do we say that something is a singleton? Using topological language. And so this one just becomes, is contractible. In homotopy theory, the role of singleton is played by contractible spaces. So you want to say this space has to be contractible. And now this has to happen for every Y. So you would say, so here you have the definition. Let's first write down what it means to be an equivalence. Is an equivalence. F is an equivalence means for every Y in B, so pi Y in B is contractible H fiber Fy. And that's just a way of saying inverse images are singletons, but in a topological way. How do you say it's contractible? Well, we had that before, but maybe I can write it down. Is contractible some space, let's say a space. Well, now I already have A and B, so I'm just going to write it in general. So a space X is contractible if what? Well, what is a contraction? A contraction wants you to contract everything to a point. There's a question.
Yeah, I was asking what's something more
Contractibilen.
And I don't remember here.
You may not have heard it because I don't know how much topology you had.
Just one year.
Yeah.
Oh,
Then you forgot.
Okay.
I don't know. Or just,
No
it's more likely you forgot.
Yeah.
Contractibility is a fairly basic notion, but I don't know if it was taught when you were there. You didn't have it? Okay. So contractibility means something like this. It means, here's my space, I have a point, and I can just sort of push everything down to this point. Yeah? But not in a one go. It has to go nicely and continuously and so on. So the way to say that is that the identity path, the identity map is null homotopic, or the identity path is homotopic to a constant path. Or in homotopy theory, what you say is this. Let's call this point here C. This is the center of contraction. Okay, so it says there is a center of contraction such that every other point has a path to it. Again, an important caveat, the selection of the path has to be continuous with respect to the point Z. Therefore, this is really going to give you a contraction. So a circle would not be contractible according to this because you cannot select the paths in a continuous way. You have to switch from going up to down at some place. So this is the third attempt. This is the one that's written in, so let's see, we now have is equiv F, and so now we define what it means for two spaces to be equivalent. Well, we just define the space of equivalences. So we say A and B are equivalent. That means, well, the space of all such things. So it's the space of F going from A to B with the information about how this is an equivalence. So is equivalence F. And if you look at Voevodsky's files in Coq or the other ones, this is the definition you will see. This is the official definition. And then Mike Schulman proved a lot of lemmas, but I mean, Voevodsky already before, and then Mike reproved them in a more readable form. You can go read both of them, which now relate. The question, of course, is how do these two notions relate? If I have this one, iso AB, which says I have f and g such that their compositions are homotopic to the identity, versus I have a map F whose fibers, homotopy fibers, are contractible. So you would want to know which way this goes, okay? So to get some idea, let's think about the following, okay? So there will be, again, so we have to get used to this. So, oh, I have to make a new page here. So we have to worry about the following: co-inhabited versus equivalent. I now have two candidates. One is called iso AB, and the other one is called EQ-AB. The space of isomorphisms between A and B, and the space of equivalences between A and B. You could think about whether they are co-inhabited, which means if one of them has a point, then the other one has a point. If that's all you want to show, that if one of them has a point, then the other one has a point, then what you need is any map here that goes in this direction, okay, and any map that goes in that direction. So you read this as a logical equivalence. This implies that, or this implies that. If I have any map going from this direction to that direction, then if there is a point in this one, there will be a point in the other one, and vice versa. That's called co-inhabited, or in terms of logic, it would be called equivalent, if you think of them as propositions. So, what the space is? Co-inhabited. There is a stronger version, of course. These are two spaces. So we have just defined the notion of equivalence of two spaces. So we could ask not whether they are co-inhabited, but we could ask whether they are isomorphic. So we could study this space. Or we could study the space of equivalences between them. So you see that this goes up one level now. I'm studying, right? This is iso between A and B, and this is iso between the iso and the EQ. So your head starts spinning a little bit at this point, I think, and especially if you try to think about this geometrically, it gets really weird very quickly, because as a geometer, I wouldn't be used to thinking, first of all, I would not even be used to think too much about the space of all isomorphisms or the space of all homotopy equivalences. That's not the natural way to go. Typically because when you look at function spaces in topology, they get very nasty very quickly. Even if you take two locally compact spaces and you look at the function space, it's not going to be locally compact, and so then you won't be able to make another nice function space, and it just gets messy. So you would necessarily have to move to some other more general setting. And I just have a feeling that this is not a very geometric thing to do. Nevertheless, I think this is a basic consideration from the point of view of homotopy type theory. If you're going to do type theory, it is entirely natural to consider function spaces in this way. So now we have three notions here: co-inhabited, isomorphic in one sense and in the other sense. And so the question is, which one holds? How close are they? So as an exercise, this is the easiest one. You just need any map that goes from one to the other. So let's try to get some map that goes from one to the other. And because I know which direction is easiest, I'm going to do right to left. So I want to go from EQ equivalence to isomorphism. Let's see. I'm trying to define a map. By the way, I could fire up coq at this point. I would go auto, and then something would happen and you wouldn't know where the map came from. So I've never been able to understand anything in coq if someone other than me did it. So if I watch somebody work with coq, then it gets much harder than if I actually do it. So coq is sort of like a write-only proof assistant. So let's try to get from EQU AB to ISO AB. Any map will do. I'm asking for anything at all. Let's give this map a name. Let's call it maybe I. Okay? I'm constructing a map. What do I have? Well, I'm going to have one of these gadgets. What is this gadget? Well, this is going to be sigma f A to B is contractible. No, is what? Is equivalence. You will see that after a while you do start to wish for coq here, equivalence f. Well, we have to write this stuff out, right? So what is a typical element of this going to look like? The typical point in here is going to be a pair. So we're going to have an f from A to B together with this, an element of this space. Now we have to look back. What is this space? So this is another map, is another map, which, let's call it G, yes, which goes from Y to is contractible. So I get here a map G, and this map goes from B to some place. Well, I can't write it like this because its type is dependent, so I have to change this. So it's a map which for any Y in B gives me is contractible H fiber F Y. Now we have to unwrap is contractible. Okay, do we still know by heart what it meant? Well, is contractible meant, I'm just going to write it here, it meant sigma C in, well, in where? Sigma C in this space, in the H fiber, such that something happens. And now you have to write out the H fiber, so this is going to be sigma C. What is H fiber? Well, H fiber is the space of all those x's in A such that there is a path from f of x to y. And then there's lots of stuff here. Why am I writing all this out? Well, what would I like to get? I would like to get an isomorphism. So I need a map from A to B and I need a map from B to A. I have a map from A to B. That's F. I need a map from B to A. I don't quite have a map from B to A, but I can get one. You see, because down here in the double index, there is an A. So I just take F from A to B, and I can't take G, but if I take, let's think of it this way. When I apply G to Y, what am I going to get? I'm going to get something which looks like G applied to Y is an element of this sum, so it's going to be a C. So this is going to be a C together with some stuff, which is this stuff here. But this C, again, is going to be a pair, so this is going to be an X together with a path, together with some stuff. And it's this X I'm after. So this is the first projection of the first projection. So this is just going to be the first projection of G. This is going to go from B to A. And now I have my candidate functions, and I would want to show that they actually do form an isomorphism. So I have to show that their compositions are homotopic. I'm not going to do this on paper. Okay? We can maybe do it later with coq, but at this point, I don't want to do this on paper.
Do we get any more intuition from whatever is written here than we would get from a coq program?
I think for me to get intuition, I would have to draw pictures. Like if I write out more pi's and sigmas, that's not going to improve the situation. Yes. So the way you could let's see if we can think about where G came from. So I start with A and B. Maybe I draw another picture. I'll draw it on a new page so that it's nice and big. Okay. So I have shown you now how you would just sort of have a dumb guess as to what your G is. And a lot of the time, if you do things in Coq and you don't already know the homotopy theoretic argument, that's what you resort to. You just sort of look and look, what could I plug in here? You plug in the first thing that comes across, and a lot of the time it's the correct one. And when it isn't, you waste a lot of time trying to prove that it is the correct one. So, how did this work? We had A, we had B, we have F. F has the following curious property. If I take here any Y, then when I look at the H fiber, now how are we going to think of H fiber? So the way to think of H fiber is like this, maybe. Okay. First of all, you take a different color. And then you say, what is H fiber? It's a bunch of X's together with their paths. Yes? So one way to draw this is to say, I have to draw a bunch of X's and then they're going to be paths. And they're going to be paths from F to Y, from F of X to Y. So one way to think of it is like this. It's maybe these X's here. Okay, here's a bunch of X's. And then when I map them over with F, they become, slightly distorted. So I've mapped them with F. So here I have a typical X. I have to make a little hole so I can put the X in there. Here I have a little X. And here I have the result, which is F of X. But it's not just this one, then I have to take all these paths. I have to consider paths from F of X to Y. Yeah? And so now it's all of this stuff. And now you say, now what is the assumption that I have about F? The assumption is that when I look at the totality of all the X's together with their paths, that's contractible. Yes? But if it is contractible, then it has a center of contraction. So whenever I look at H fiber Fy, so this is the strange thing that looks like this. It's a bunch of X's together with their paths. So it's an X, and then there is a path. It's wrong to draw this path out of X. It's a path which goes from F of X to Y. And then maybe there is another one, but it has a slightly different path from F of X to Y. And then maybe there is another X prime, and this one has its own paths from F of X prime to Y. Okay, and then there is X double prime, and this forms something. But it's contractible, which means somewhere in there, there is a center of contraction. There has to be a center of contraction, which everything else contracts to. Okay? What are we trying to get? Well, we're trying to get a map going in the other direction. So, starting from Y, we need to produce something in X. Something canonical, so that it's a map. What is there that's canonical about this? It's the center of contraction, right? So, your assumption that the fiber is contractible is, for every Y, gives you this center of contraction C. Well, actually, it gives you a pair. The center of contraction is C together with the chosen path. But you just take the first component. And you hope that that second path, that path that you have there, that it's going to come in handy when you try to show that you did the right thing, which is exactly what is going to happen. Okay? That would be the best picture I can draw at the moment. Yes, so that goes in one direction. Now, the other direction, you got stuck when you try to do the other direction. What would be the other direction? Well, you would say, start here, go there. And the reason it's stuck is that you have to do something a bit smarter. And to get the smarter thing, we have to consider something else. A fourth attempt. If I have two maps, A and B, from F to G, then it's one thing to say that there are isomorphisms. So let's call these one, let's call them something. Let's call them, so we have F composed with G, there's a homotopy going like that. And so let's call this one S. So why am I pretending that this is a map? Recall, what is this homotopy business? This means homotopy. So a homotopy means for every point something happens. So it's a map. Okay. So this is a map. I'll call it S, and I'll call the other one R. So if you stare at this, it should remind you of something. It should remind you of the following situation. Given two categories C and D, and I have F and G, and I have natural transformations. Now it looks. See, I want to get to an adjunction of two functors. Okay, so let's say, well, it's polite to make F the left adjoint. So if you want to make F the left adjoint, we would say, well, there is going to be an eta, which goes from the identity on something to G composed with F. And please correct me if I'm wrong. G composed with F. This would be a natural transformation going from the identity on C, presumably. Okay, so you would want that, and you would want the other one would be F composed with G on the identity on D. So this is beginning to look a little bit like that, except that here I have, once I go in one direction, the other time I go in the other direction, and here I'm going both in the same direction twice, you see? Well, that's just an accident. Paths are invertible, so I can always turn this around. If I have R going from G composed with F to the identity, if I have a homotopy like that, I can just turn all the paths around. I'll get it to go in the other direction. So this is irrelevant. So S here is playing the role of epsilon, I suppose, and R is like eta to the -1. Well, but eta to the -1 only makes sense if eta is an isomorphism. Yes. In fact, you should think of S and R as being invertible maps, because you can invert paths. So the corresponding situation is not a general adjunction between F and G, but an adjunction which is also an equivalence. So that's called an adjoint equivalence. Which means I have an adjunction, F to G, and the unit and the co-unit are natural isomorphisms. That is stronger than saying just I have eta and epsilon, which are natural isomorphisms. I also have this thing here. So that part is missing here. I want to say there is a special relationship between F and G. Because S and R are giving me the fact that I have two natural isomorphisms, like eta and epsilon. But I also want to say, maybe, that would be a stronger notion, that F and G are adjoint. And you can do that on the other side as well. The only question is how. Well, there are like 25 versions of, there are 25 ways of saying that F and G are adjoint functors. You just have to pick one that applies in to the that makes sense in homotopy theoretic language. So Let's see if I can get this right. I think I have to look at the coq file, otherwise I'll get hopelessly confused. I don't have it on paper with me. Yes, I do have it on paper with me. Okay. So there's something called the triangle identities for the unit and the co-unit. What are they? What do the triangle identities say? So I can never remember them, so I always have to recreate them. So let's recreate them together, okay? So I have here, let's take it at a particular object. So suppose we have an adjunction like that. Fg. And I have my unit, eta, and I have the co-unit, epsilon. Like here, up here, okay? So now you start playing around and you say, well, let's take some object and then we can have x, and then here I'm going to have eta at x, and then I'm going to have g of f of x. Well, I could, for example, I could apply f to this. And if I apply f to this, I get f of x, f of eta x, f g f x. But now you stare at this and you say, well, this is fg, and here I have fg. So in fact, if I look at epsilon at fx, it's going to go to fx. And here, see, I say, wouldn't it be nice if this were an equality? In fact, that is a triangle identity. And this is a way to characterize adjointness. To say that two functors f and g are adjoint is the same as to say that I have two natural transformation, epsilon and eta and epsilon, such that, and now I can write it without the x, such that if I have, so I'm going to have f eta goes to f gf epsilon f such that this triangle commutes. If you're a homotopy theoretic, then you will stick in a suitable homotopy here. There's another one which you get if you reverse the roles and you start with epsilon and you play around and you get another one. I'm not going to draw it, but this is one of the triangle identities. So we try to do this in a homotopy world up here, the same thing. Yes? We have to figure out what these things are. So I start with A, B. I have two maps F and G. They're playing the roles of functors now. Yes? Okay, so but if they're playing the role of functors, a functor maps objects to objects and morphisms to morphisms. So a map takes a point to a point, but what's a morphism? Well, a morphism now is going to be a path. So does a path, if I have a path P from X to Y, I want this to be taken to some path which goes from f of x to f of y. And if you look at the coq files, this is one of the first things you do. It's called map f. It's called map f, map fp. I'm going to use the following notation on paper, f dot p. Well, it's not really paper, but so f is acting on p. In coq, it's called map. So you say map fp. It just takes the path in one space. Here's A, here's my path B, here's B, I have an F. Well, clearly then I should have some path. F should take this path to that path, so that's f dot P. Okay? Yep, so this really is like a functor. The F and the G are like functors. Then we have the unit and the co-unit. So it's going to be a little funny because my units and the co-unit, the S and the R in this case, they're invertible. And as I warned earlier, while S does look like the co-unit, the unit goes the wrong way. See, R and eta, they go the opposite ways. So maybe I'll have R to the minus 1 instead of R or something. But I will now, so Mike wrote in the Coq files, he wrote R in this way. When I looked at this, I was tempted to turn it around, just so that it looks more like the usual adjoint equivalence. So, and maybe I will do that. But for the time being, I want to stick to what's in the file. I'll use this R. So maybe I have to beware that eta maybe gets turned around or something. So I have an S. The S goes from, let me write it out now. How is S? Well, S for every y in B, S gives me a path from f gy to y. And then I have an R, which for every x in A gives me a path from g of f of y. This should be x here. And this one should be wiggly. So now we explicitly see what the S and the R are. Okay, now we go back and we simulate what happened here. So I started with what looks like R to the minus 1. Yes? Or maybe I can just go here and I say, I take another color. And I'll just start writing. Okay, I look at this one here. It says, so this is going to be little f. Eta is going to be like R to the minus 1. This is going to be S. And this is going to be F. Yes? And so this should be the identity. So F R to the minus 1 and SF. Oops, wrong. Go away. Okay. So, oh, now I forgot. F to the R minus 1 SF. F to R to the minus 1 SF. F R minus 1 composed with SF should be the identity. What kind of identity? Should be the identity. Aha, okay, so this is maybe not so clear now. It should be identity on F. So there should be really a homotopy here or something like that. So there should be, this should say.
The composition should be the other way around.
Yes, thank you. The composition is the other way around. Okay. So it's SF. But let me just write things. So SF, S composed with F, for a particular X, I'm going to have, let me draw a picture. So I have X, then I have F of X. So I want to do the, I'll do, which one do I have to do first? Well, it doesn't matter. I'll do this one first. So what is this SF? This means I'm going to go from f of g of f of x. Okay, so I start here. I have f of g of f of x. I'll draw a picture first. I think it's better than to just try to write it down. Okay. I have f of g of f of x. And then, you see, s will take me from f of g of anything. So if I apply s at f of x, that's going to be a path which leads to f of x. Okay? That's this part here. Now I want that part here. Okay? So this is f to the r minus 1. And it starts with f applied to x, clearly. So I say I have f applied to x. So on the side I'm going to do this. So I have, I'm confusing myself here. I have to look again. So f FGF. So f FGF. On the side I have f of x, f g f of x. So r goes from gf to x, and if I act with f on it, oh, it's in the right direction. Oh yes, now it is like this. Okay, so this would be f acting on r, it would be like that, but I want to go in the other direction, so I have to do f acting on r turned around. Yeah? And so now this stuff has to be equal to the identity. Well, what does that mean? You know, well, we have to say there is an identity path here. Yes. Okay. So this is the identity path. And as I warned earlier, I'm going to say not that this diagram commutes, but that this stuff is homotopic. So I'm now saying if I take SFX concatenated, we don't have a notation for concatenation, but in the Coq files is this. So I take this path, then I take that path. Sorry, the concatenation goes the other way, so I have to write here. F dot r to the -1 concatenated with this has to have a path to x, to the identity path on x. Something like that is going to happen. So there's going to be a simulation of what is normally called adjoint equivalence in category theory. It exists in homotopy theory. And here is an observation. This is an important observation. You can prove that these two guys are co-inhabited. That is to say, we went from one, we indicated how to go from right to left. It's also possible to go from left to right, yes, but it's not obvious. But what happens is that you want to go through this third option, which is not just isomorphisms, but adjoint equivalences. So I'm going to write this down now. So we want things to go this way. What's this picture doing here? It's out of order. So on one hand, we have isomorphisms. Then we have the equivalences, which means homotopy fibers are contractible. But we can now consider a slightly more important notion, which is adjoint isomorphisms. What is this adjoint iso? Adjoint iso, AB, means, well, you have a map F from A to B, and you have a map G from B to A, and you have a homotopy going from, now let me not confuse myself, F composed with G to the identity on B, cross G composed with F to the identity on A. This part is the same as iso, but now I add something. I add the triangle identity. Cross, now I want the triangle identity. So the triangle identity was what? Can we see what this was here? This is the out of order picture. So it looks horrible, right? So you have to say for every x, I have this stuff here equals that stuff there, and there is a -1 here. So it actually turns out this -1, you can put it on the other side, first of all, without loss of anything. So you can just say SFX has a path to FRX. So you want to say something like this. And I'm going, so this would be, in our case, it would be, well, it's going to get complicated because now I want to say there is an S and there is an R. Oh, this particular S and R. Well, okay, so I'm going to write this. So here it gets more complicated because now this is my S, and this is my R. Which one is S? Which one is R? FG is S, yeah, this one is R. And now I want to use them. So I would really have to write here the sum S, the sum R. Okay, forgive me if I'm not writing this, but I would have to write now dependent sum S is an element of this thing. Dependent sum R is an element of this thing. Cross, and now I want to have the triangle law. I'm just going to write the triangle law. Yeah, which is going to be of the form for every X something happens. That thing on the other side, on the other page. Okay? This is stronger now, of course, because this space, you see, this is a space which, apart from the isomorphisms, it's telling you also that there is some nice property. So, from the point of view of category theory, this is a natural notion to consider. I mean, category theorists have considered adjoint equivalences. But they also know a very important fact. Every equivalence can be turned into an adjoint equivalence if you change one of the unit co-unit pair. You can change it slightly, it becomes an adjoint equivalence. You can always do that. So whenever you have an iso, by the way, of course, if I have an adjoint iso, then it is an iso. Because I just forget this triangle law. But, importantly, it also goes the other way around. If I have just F and G with some S and R, then if I change R slightly to something else, I can make sure that the triangle law holds and I can go in the other direction. So I get something in the other direction. Whereas here, I have an actual equivalence. Now, at least in Mike Schulman's file, I think this is not checked. He has a comment saying it would be nice to check this. I haven't plowed through Vladimir's files to see whether he actually did it. But I think here we should be having an equivalence in the sense of EQ.
The only thing we need is a map upwards.
We need a map in which direction? Well, we need a map.
To Iceland to EQ, because we need the map from ISO LB to EQ. So.
You want a map upwards. Oh, you're still going for these two who are co-inhabited. Yes, of course. But if you get an equivalence here, then of course you will have maps in both directions and more. Right? You will know the spaces are equivalent. So yes, so you want a map upwards. Yes. Definitely. Okay, so that's how much I wanted to say. And now I just want to look at 5 minutes for how this is done in Coq. Just so that you see that it's not terribly different from what I've been saying. So, we go to see they're here. No, I think it's this one. Let's have a slightly larger font. So we start with the notion of is equivalence. And when you see these parentheses, this means this is an implicit argument, you don't have to specify it, and so on. So given spaces A and B, a map F is an equivalence if for all Y and B, the H fiber is contractible. I can ask, what is the H fiber, for example? And it tells me that the H fiber is this thing here. You have to look here. It's hard to know where to look here. This is the dependent sum. It says the dependent sum of such x's in A so that there is a path from f of x to y. Mike recently changed all the notations, so the paths are now written like this instead of the old way. I don't like it, but I'm not going to complain about syntax, otherwise we'll just keep complaining about syntax. Okay? And then what is an equivalence? Well, the space of equivalences between A and B is the space of maps. Now we're going to call them W for equivalences for, well, this is funny. They're called W because this used to be called weak equivalence and then we got renamed equivalence. So W from A to B such that it's an equivalence. So this is what I wrote as a dependent sum, but in Coq it's written like this. And we're going to have a notation. So A, this double wiggly thing, means that A and B are equivalent. It's the space of equivalences. Okay? So here's the first one. If you have an equivalence, oh, this is just a minor point. An element of this space, equiv AB, is a pair. It's a pair consisting of a W together with something in this space is equiv W. So really, it's not a function. It's a pair whose first component is a function. And this magic here is just telling Coq that whenever you see a weak equivalence used as a function, just project out to the first component that use the function. It's an implicit coercion. So I don't want to stop here. Here's a little tactic that we're going to skip because we're not going to look at proofs. Here's a proof that the identity is an equivalence. So maybe we go through one, okay, just to see how Coq works. So it's saying we have an A, which is a space, and you are supposed to produce an equivalence from A to A. And since an equivalence is an element of the sigma type, the way to do this is you specify the first component, that is the map, and then you are obliged to prove that really is an equivalence. So I say, yep, let's use the identity map on A. And it says, now you have to prove the identity map is an equivalence. And so then you go and do, and something comes out, and then you do this, and that, puff, okay? And you don't know how it got proved. Then here's the inverse. Okay? That's the inverse we were trying to get. If I have an equivalence W from U to V, then maybe, oh, we didn't do that. Every equivalence has an inverse. Actually, we skipped over that part, but do that as well. But that's the G that we were getting out of that, actually, it is, yeah. If I have an equivalence W as a map from U to V, how do I get a map from V to U? That's the projection of the projection. See, it's the projection of the projection, but there's a second projection here now. I had just the first projection. Why did I have just the first projection? PR.
Because it was a pair, what you said.
Sorry?
An element of this equivalence is a pair.
Oh yes, an element was a pair for me. Yes, that's what. Yeah, okay. I would like to get to. There's a billion tactics here for manipulating this stuff. I would just like to get to the triangles so that you see where how the triangles are written down. Okay, we try to understand the triangle, and then we. Maybe a little more, and then we stop. So, it says, if you have a W, actually, sorry, this is the wrong one, this one, I want to get to, there's lots of stuff in here. I want to get to this. It's an adjoint equivalence. Let's see if we can understand its adjoint equivalence. There. F is an adjoint equivalence means, let's read the definition. Okay, so it says, I'll read it in the logical form, not as a space. So, to say that F is an adjoint equivalence means that we have a G, which goes in the other direction, and we have a map is section, which for all Y gives me a path from F of G to Y. So that's what used to be my S. Let's go back here and see. Here, that's the S. For everybody, for every Y, I have a path from f of g of y to y. This one. He's calling it is section instead of S. And there's is retraction. And here's the triangle identity. Now let's see, is it the triangle identity? This is F acting on Rx. F acting on Rx is down here. And this is S applied to f of x This is S applied to f of x. So his paths go the other way around, but that's irrelevant. It is the triangle identity. Okay? You can actually understand this sort of thing when you see it in Coq. And now there are going to be some proofs. For example, if I have f, and I know that it is an equivalence, then it is an adjoint equivalence. And he just writes down the proof. Well, how can he write down the proof? To show that something is an adjoint equivalence, so here's my W, and I want to say W is the adjoint equivalence. Well, what's the inverse? The inverse is going to be the inverse map, the one that we talked about. And then he already proved all the lemmas he needs to prove this, so he just uses the fact that inverse dissection, inverse retraction, and the inverse triangle identity. These are some lemmas that were proved somewhere up there that I'm not going to look at. Then then here's the type of all adjoint equivalences. It's f from A to B such that is adjoint equivalence f. This is slightly different from what we had, because I wrote, well, first of all, I wrote ISA instead of edge equivalence. But mine is f and g such that stuff. Well, it really is the same, because for him it's f such the stuff. But this stuff here, if you look at how it continues, it's up here. F and then g such that stuff. So it's the same thing. Here he goes from the adjoint equivalence to equivalence. So which arrow is that in the diagram? From adjoint equivalence to equivalence means go from here up there, huh? Like that. And you go. So, if you do this in a book, you are never going to do it at this level of detail. If you do it on paper, I guarantee you, you're not going to do it in this level of detail. This is all detail, all the way, okay? So, I'm being maybe a little funny by not showing you the proofs, but as I said, I can never follow other people doing proofs with Coq. So you say, well, it's supposed to be an equivalence, so this H fiber is supposed to be contractible. We're going to contract the GY and this section, and then we're going to apply something. I mean, just do this in the privacy of your own bedroom. Okay, so there are lots of lemmas here, and I just want to show you what the conclusion is afterwards, because it's very useful. This one, it's very useful for showing that things are equivalences. This is now the final form, which says if I have an F and a G, and they are isos, you see? Here is one inverse, here is the other inverse. So this data up to here is the same as saying we are here. Yeah? If I have this stuff here, then I can show that F is an equivalence. That is to say, I can get the crucial part of this. So that goes from here to there. And it's just, how do we do this? Well, let's see. We take F and G and the section and the retraction. So we take the stuff from here. It does not satisfy the triangle identity. But as I said, there is a proof that shows that you can make them satisfy the triangle identity by changing the section and the retraction. And that's what this adjointify does. We skipped over it. So now I'm down here. And now because I'm down here, I can go up there via this is adjoint to equiv. So that's very nice, because that means instead of proving that homotopy fibers are contractible, I can tell you it's really nasty. You don't want to prove a lot of theorems of the form homotopy fibers are contractible. You're going to hate it. You can just, to establish that there is an equivalence between A and B, you just provide the maps F and G, and you only check that they're inverses of each other. You don't have to worry about the triangles, you don't have to worry about contractibility. And so then he gets a lot of lemmas out of this. For example, that the inverse of an equivalence is an equivalence, and that if F is homotopic to G, then if one of them is equivalence, then so is the other. You get the 2 out of 3 properties for equivalences from this. That if you have a composition of 3 maps and 2 of them are equivalences, then so is the third one. 1, 2, 3. And then stuff. More. Okay? So that's the sort of thing you do if you do the homotopy type theory. At the beginning, I'm hoping we can do something much fancier later on. Any questions? So you may venture into looking at these files. Egbert is going to. Everybody else is not going to. Okay. You already did. There you go.